Okay, so we start this by just reminding you that in as per Flory theory, the nu, the Flory exponent, the nu r goes as n to the power nu is equal to 3 by 5, which is equal to 0.6. But there are more accurate analytical theories which calculate nu. I mean, they are much more intense, but they calculate nu as 0.588, which is equal to 0.59, and not much difference from 0.6. But yeah, so the more accurate values is this, but we shall primarily use nu equal to 0.6. So in this module, so we will be discussing basically the idea of correlation blobs and correlation length, and that is valid for semi-dilute solutions, and that's where the idea of correlation blobs comes along. So what is that? We'll get to see about it, but just to as a quick reminder, we tell just of the previous module of this week. I should just remind you that the size of a polymer chain in a good solvent with total number of monomers in a polymer chain much greater than xi t, xi being the correlation thermal blob. So this is the length scale of a thermal blob, and then r, the extent, a measure of the extent of the polymer chain, can be written as xi t, which is the length scale of a blob, thermal blob, into number of blobs. N is the total number of monomers in the chain, by gt is the number of thermal blobs in the chain, and that to the power nu, the Flory exponent. And when you replace zeta t and gt, you basically get this b into v by b cube. So this is v, this is b cube, 2 nu minus 1, and to the power nu. And just to remind you also that gt can be written in terms of more microscopic quantities as this, and the thermal length scale, blob length scale, thermal blob length scale can be written as b to the power 4 by v, and you can revise this in slide 6 and in the previous lecture. The question, the physics question that we are asking in this small module is that as one adds more and more polymers to the solution, so this was all about one polymer chain, but here we are adding more and more polymers to the solution, and the polymers start interacting. How is the polymer chain size and the distribution of monomers of a single polymer which is surrounded by other polymers, how does that get affected? Does interchain interaction affect the distribution of monomers in a polymer chain? So that's the question we are asking. That's the physics question, and for that we shall do the next analysis, which I'm going to present. Okay, so first is the question is, when shall polymer chains start interacting? When shall different polymer chains start interacting? So when you are in the dilute polymer chain, dilute polymer limit, then you essentially have one polymer floating around in solution, and then very far away, non-interacting, very far away, another polymer chain basically floating around in solution. But now you are adding more and more polymers, so the concentration is increasing. And if the monomer volume fraction, okay, so when the chains start to overlap, when the monomer volume fraction phi is given as small n is the number of polymer chains, capital N, number of monomers in a polymer chain. So this is the total number of monomers in the entire system with volume V box, right? So suppose that's the volume of the solution in a beaker or in a test tube or wherever. right? This is the total number of monomers in n chains, and b. So this is the monomer volume fraction, right? So where b cube is the basically excluded volume of a polymer chain in a thermal solvent, of course, right? So when phi is greater than the overlap volume fraction, then monomers start of different chains start interacting. Question: what is, how do you estimate the overlap volume fraction? So overlap volume fraction, phi star, is basically the number of monomers in a polymer chain, p cube, volume of number of monomers in a polymer chain, divided by r cube. What is r? R is the pervaded volume. I mean, r is the radius of the from which you calculate the pervaded volume. So pervaded volume has been discussed previously, and so this is basically a comparing monomer volume fraction. When the monomer volume fraction becomes equal to the phi star, the overlap volume fraction, that means that the overall concentration of monomers in V box, the overall monomer concentration in V box becomes equal to the number of monomers, or rather the monomer concentration you will find in a pervaded volume. So if that becomes equal, that means that basically all the polymer chains are touching each other, and it has become space filling. So if you like, if R is the pervaded volume and N is the number of polymer chains, so then this would become equal to V box. So that means all polymer chains, all pervaded, the box's solution is full of N monomers, they are touching each other, all the pervaded volumes of n monomers is equal to V box, and it is at that point that phi will also become equal to pi star, right? And and then basically chains start interacting with each other. uh, just to tell you, though it is not often used, one can also define something, volume fraction, the polymer volume fraction, but calculated the way you would do it for colloids. So how would it do for colloids? So if the colloids basically suspended, Brownian particles suspended in a fluid, what you would calculate is the volume of each colloid, number of colloids divided by the total volume of the solution. And then that would be basically N, number of polymer chains, pervaded volume, whole cube, right? So basically you are, I mean, of course, within a polymer conformation there's a lot of space. It's not like a colloid, and a colloid is a dense object, right? Inside that there's no solution, but within a polymer there can be a lot of solution. But still, if you take the pervaded volume, I mean, you calculate the pervaded volume as r cube, and r cube by V container box, then you call it the basically polymer volume fraction, but calculated in the way of a colloid, the way you would calculate it for a colloidal system. So it's the colloidal volume fraction for a polymer. So that is sometimes used in literature. So just for your information, okay. But we are more interested in more standard polymer literature. When phi is greater than phi star, when the concentration, when the monomer volume fraction has become greater than phi star, then there are more than one polymer in a pervaded volume of R cube, and more than NB cube monomers in volume of R cube, right? So there is more than that. So the R cube, a pervaded volume, has monomers from multiple, could have monomers from multiple chains. So in that case, R is the extent, measure of the extent of the polymer, becomes xi t, right? So basically, have I missed something? Okay, yeah. Okay. Okay. Yeah. So here we are using the standard expression R for a thermal blob, the thermal blob expression, and we are of course replacing XIT and GT. So this is what we get, and phi star equal to NB cube by R cube, right? So basically we're just touching. So basically that's the dimension. That's the dimension of a polymer when they just start touching. Then R would be calculated like this, and you replace this the expression for R cube using this, and then when you substitute everything and do the calculation correct, then what you will get that phi star depends upon n number of monomers in a chain 1 minus 3 nu, and when you calculate that, what you would get is phi star goes as n to the power minus 4 by 5 if nu is taken to be 3 by 5, and equal to, so minus 4 by 5 is 0.8, and this is will be n goes as 0.76 if you take nu to be 0.588. But when monomer concentration is greater than phi star, in start interpenetrating, and then you call it a semi-dilute polymer solution. Just to remind you that even when the monomer volume fraction has become greater than phi star, it's still much less than 1, which is close to a melt case. Here all, so if it is equal to 1, then all the space is basically filled with monomers. Uh, here this is much less than 1, means there's a lot of solution in between the monomers still. And then when you are going in the semi-dilute limit, to understand how the monomer is distributed over different length scales, we have to introduce the idea of zeta, which is called the correlation blob length scale. And understand that zeta by default, I mean, it depends, but zeta for in a good solvent is greater than zeta T, the thermal blob length scale, right? So, before we go ahead, just for comparison, let me remind you here for the good solvent case, we use phi star goes as NB cube by R cube, and for R cube we used this expression after n to the power nu. But if you had ideal chains, the theta solvent, then this phi star would be NB cube by R cube, where R would go as n to the power 3 by 2. R cube will go as n to the power 3 by 2 because R goes as b to the power n to the power half for the theta solvent, the ideal chain case. And in that case, phi star would actually go as 1 by root n. And when phi becomes greater than phi star theta for theta solvent, then chains start interpenetrating, and you get a semi-dilute solution. But here, so this was just as a diversion, and just to remind you the difference in scaling for the phi star goes how phi star goes as a function of n for a good solvent, and this is for a theta solvent. But we, after this, correlation blobs will be discussed more in the case will be discussed for the case of a good solvent case. So we are basically continuing from here. This is just a reminder that things will be different if you have a theta solvent. Okay, so the idea of a correlation blob length scale. Now suppose these are long polymer chains, okay, and they have, as you see, started touching each other. So we are in a semi-dilute solution. So the idea is monomers interact with, mostly monomers, this is the center of different chains, right? They interact with monomers of the same chain, and only if you go length scales above zeta, the correlation blob length scale, do monomers from different chains start interacting with each other. So you see that when you go greater than this length scale zeta, the red monomers and the blue monomers have started touching each other. The red monomers and the green monomers have started touching each other. Here, the red monomers and the black monomers have started each other, and so on and so forth. And between the chains, there is, of course, solvent. So, what is the message? Only at distances greater than zeta, or at distances zeta from the center, do the red monomers meet monomers from other chains. And since the polymers are touching, we are in a semi-dilute solution. The correlation volume, what is the correlation volume? If you take zeta cube, you will get an estimate of the volume of each of these, and those are called correlation volumes, are space filling with some overlap, because we are in a semi-dilute chain solution. And now suppose this is the same schematic diagram as before, with this being the correlation blob length scale, and a polymer with NC monomers. Suppose the total length of the polymer is NC, and I have intentionally put this in C just to remind you. Usually we use N as the total number of monomers in a chain. Here we are using NC, and the reasons for it to avoid some confusion coming up soon. So a polymer with NC monomers has G monomers within zeta and N minus G monomers outside of zeta. So if you draw a circle from the center of the polymer, define a length scale. So basically I'm saying that G, so as different from GT, GT was the thermal blob length scale. Here you have a zeta which is greater than the thermal blob. So basically what you have, if this is your polymer chain and you have a monomer at very small length scale, and at this scale you have a thermal blob and a large number of thermal blobs, self-avoiding random walk of the thermal blobs gets you to the zeta length scale. And above the zeta length scale, monomers from different polymers start interacting. So G monomers has GT thermal blobs, and at length scales greater than zeta T, you have interaction. Now, just to remind you, this is basically from slide 9 of the previous module of this lecture this week, where we're discussing thermal blobs. This is the extent of the polymer. In the coil configuration, you are talking about a good solvent, and these were the formulas which were used. But now what I'm saying is, so these were the formula. The N was the total number of monomers in the chain. But now you have a self-avoiding random walk of thermal blobs up to the length scale of zeta with G monomers. So just replace N by G in this formula. So replace N by G in this formula. Just to remind you, NC is the total number of monomers in a polymer chain, right? And then you can write zeta, which was equivalent to R here. So R equivalent to zeta is the same formula as you have seen previously, where N has been replaced by G. So looking at the correlation blob length scale, number of monomers within a correlation blob, right? So this is the relation. And also you have phi, the monomer concentration, right? This is G, number of monomers within a correlation blob length scale, B cube by correlation blob length scale cube. Right? So this is the monomer concentration within a correlation blob. This in general will hold true. And if you have, so you have this equation and this equation. So from this equation, what we are doing is taking this expression to the left hand side of the equation. So zeta by B, if you like, this B comes here, then this B cube goes to the numerator, V comes down to nu minus 1 is intact then, because you have already inverted it. is G nu. And now you can write G in terms of zeta by B basically. So there's this nu. So here there's no nu but 1 by nu, and 2 nu minus 1 by nu. Right? So you get an expression of G in terms of the correlation blob length scale. Number of monomers, and how does it vary with the correlation blob length scale. Right? Now we are using this formula. We are substituting the expression of G in this formula. So this is the phi. Now G has been replaced, and now you have a in terms of zeta, right? And you already had beta cube and zeta cube sitting here. So now you are getting phi in expression of zeta, right? And if you substitute all of this, what you get is, see, these are microscopic quantities. B cube V is microscopic quantities. This is of course the Fourier exponent, and you get the scaling relationship of phi with respect the monomer concentration in terms of the correlation blob length scale. Invert the equation, basically inverting the equation, and you get the correlation blob length scale. That is the thing which was unknown. Monomer volume concentration is basically you add, you know how much monomers you are adding in a solution. So that's something which you can control, right? Whereas this correlation blob length scale is a mental construct for analysis, and this is the quantity which you don't know. This is the quantity which you can control experimentally. So what you are getting to know is when you substitute nu and so on and so forth, you see that the correlation blob length scale goes as phi to the power minus 3 by 4. So if you put it in the denominator, if basically if phi increases, monomer concentration increases, the correlation blob length scale decreases. Why? Because as phi increases, overlap increases, the number of monomers interacting with each other increases, and as a consequence, the correlation blob length scale zeta decreases. Now, if we substitute the expression for zeta in this expression, then you get phi as a function of G, right? Because you have replaced this zeta cube in expressions of yeah, basically you have replaced so substitute the expression of zeta, and then what you get is G. I mean, and do some algebra and reorganize terms, and you get G in terms of phi. Right? So this is another quantity. How many number of monomers are there within the correlation length scale? That is another thing which we don't know. Whereas phi, the monomer concentration, is something which you can control, which you know how much monomers you're adding, and that you see that decreases with phi as minus 1.3. So what is the message? As phi decreases, yeah, so as phi decreases, G decreases. Number of monomers in the correlation volume, of course, decreases because correlation length itself is decreasing. So a polymer with NC monomers in the entire chain, but a correlation blob length scale of G, zeta, so G and zeta decrease as phi, the monomer volume concentration, increase, right? So at R less than zeta, you have essentially a self-avoiding chain of thermal blobs. At R less than, at R which is less than the thermal blob length scale even, and thermal blob length scale is of course smaller than the correlation blob length scale, then the polymer conformation is an ideal chain. But at length scale at R greater than the correlation blob length scale, the monomers are also being pushed by the monomers of other chains, right? The red interacting with the blue, and hence, and that essentially compresses the monomers of the central chain of this chain. So this monomers are basically being also pushed back by monomers of other chains surrounding this blue polymer, and excluded volume repulsion is screened by the overlapping chain. So this is the key idea. So above the correlation uh, blob length scale, the monomer conformation statistics again becomes ideal as excluded volume repulsion is screened. So if you had to plot in the log scale again, right, um, number of monomers, and you're going along the contour and it's constantly increasing, GT, the thermal blob length scale, the correlation blob length scale, and NC, which is the total number of monomers in a chain. And on the y-axis, this is one monomer length scale. This is the monomer length scale. And then this is the thermal blob length scale. And this is basically, sorry, this can't be zeta, the T, this has to be zeta, just zeta, the correlation blob length scale without the T, right? Here we're increasing number of monomers as you go along the contour. Here it's a length scale, and R is the total size of the polymer. And here, luckily, I have not drawn it, this part, which was wrong. So it starts from 1, then up to the thermal blob length scale, you have ideal change statistics. Beyond that, you have a self-avoiding chain. You have a self-avoiding walk of thermal blobs, and once you go above, this T is wrong, above the correlation blob length scale, you again excluded volume is screened, and you get back your ideal chain statistics is n to the power half, right? Where NC is the total number of monomers in a chain. So so that's the point, and then we will come to tension blobs and Pinker's blobs.